we continue the KUKA on kinematics system. Last video you already see the kinematic, forward kinematic and inward kinematic. For last two videos, it's really cool, right? But the more important thing, I want you to understand how they work and how the DX convention work behind the scene, not what you saw on the video. I don't want you just saw the video and say, oh, it's cool. No, the thing I want to know is the how to do that, how to calculate the forward inward kinematic and inward forward kinematic and inward kinematics for the any arms, not only the KUKA arm. For example, in the future, you can see the Kino arm, UR10 arm, and you can do the similar way to analyze the kinematic for that arm. It's the same thing, right? Yes, I want to make this video to show you how to design the DX convention and solving the kinematic for uh, the robot arm. So right here, the KUKA arm, they have 6 arms. Okay, let's go. Forward the kinematic. I hope you understand something a little bit about the forward kinematic, inward kinematic, and DX convention. Let's briefly remind you how about the invert and what the invert kinematic and what the forward kinematic. I mean, we for any robot arm, you know for example, right here we know the angle for each zone, and we got the final position and orientation. And inverse means you know the uh, position orientation. You had to calculate the angle of the zone for each zone. Okay, that's the backward, right? Forward, you know the angle zone, you calculate the position orientation. Back and invert kinematic, you know the position orientation, and you go calculate the angle of the zone. That's it. So for this example, and you know they have the revolution right here, 6 revolutions right here, and how we design the kinematics, forward kinematics system right here, and how we first thing first, you have to know how to put the frame on the each zone, how to use the DX convention and fill in the DX convention table before you jump to calculation and coding for the simulation, right? So I hope you remember the DX convention. What the DX convention? DX convention is system that have designed the coordinate frame for each coordinate frame at each zone. And you know, for example, right here you have the 1 frame 0, frame 1, frame 2, frame 3, frame 4, 5, 6, okay, and frame G, arrhythmic reaper. And they give us the transformation matrix too. For example, right here, this means the relation between the frame I minus 1 to frame I, 2 frame together. Right here, look at this picture. You can see, for example, they have 2 links. Okay, we put the 2 frame coordinate as I minus 1 and I. So what's the relation between 2 frames and how to move this frame to this frame, this frame. Okay, that's look at this frame, and you see it to move from here to here and match this frame. You had to rotation alpha first and translation A and rotation theta and move up D, and you get this frame. So they represent for the transformations, homogeneous transformations from this frame to this frame. Okay, and you see look like what I talk I say they rotation on for they go to translation and rotation and translation. You got the homogeneous transformation matrix right here, the answer, the result right here. You see for 2 frame you have the cosine theta I S means sine and C is cosine. And this transformation matrix is really useful for us to know the location right here and to know the orientation matrix right here. So, okay, go back to the example. In the DS convention, you have to note 4 parameters really important to fill in the table DS convention: alpha, A, D, and theta. Alpha means the angle between the Z minus 1 to Zi. For example, frame 0 to frame 1. Okay, frame 0 to frame 1. It means alpha right here means I had to calculate alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, 6. Okay, for example, how the alpha 1 right here, we have Z1, Z2 is matched together, so alpha 1 equal 0. Okay, for example, alpha 2 from frame 1 to frame 2, and you have the Z1, Z2 right here. We had to rotation from Z1 to Z2 is mean power 2, right? It means power 2, but clockwise, so it's minus power 2. And from frame 2 to frame 3, how about Z? You had Z2 and Z3 is parallel, so it's 0. For example, from frame 3 for frame 4, you have the Z3 right here and Z4 right here. So you have rotation Z3 to match to Z4. It means you have it's power 2, right? It's minus power 2. In similar from Z5 to Z4 to Z5, where Z4, Z5 is you have to rotation Z4 to Z5 mean power 2, but counterclockwise power 2. How about Z5 to Z6? It means rotation Z5 to Z6, it means power 2 clockwise. Okay, that's alpha. And A is mean the distance between the Z, I minus 1 to Zi. For example, I minus 1 right here is for the A1. How do you know the A1? It means A1 is mean from the Z0 to Z1, but along S. Measure along S. I mean, right here is mean from A1 is equal 0 because Z1 and 2 match together. For example, Z from 1 to 2, how about the A? 1 to 2 is mean Z1, Z2. Z1, Z1, Z2 right here. So the distance right here. We'll continue, for example, from this frame 02 03, we have the frame, we have the distance A2 right here, A2, okay. How about the D? D is a link offset distance between the I minus 1 and its I. D I minus 1. For example, for the link 1, right here, we have the distance from right here, or 1 is minus 1 from right here. from h0 to h1 is d1. Okay. How about the and that about another example? For example, d3. For example, we have the d4. D4 right here resemble D4. We have the how about D4? That's D4 is the distance between the S3 to S4, S3 to F4, S3 to F4, D4. Okay, it's really easy. Let's look at and do step one by step. Okay, you can find the A, B, A, and D4 link between two coordinate frame together. So, and last parameter is mean the joint angle. Right here we have the 6 revolutions. So the angle for each one, for example, you have the Q1. For example, we have the for zone 1, you have Q1, for zone 2, we have Q2, Q3, Q4, Q5, Q6. How to know the Q1? Right here, Q1. Q1 is mean the angle between the S minus 1 to Si. For example, Q1, it means the S0 to S1, right? S0 to S1, in this case, you see S0 S1 is parallel, but zone 1 itself, they rotate the Q1. So when we fill in the table, we write the Q1, okay, or theta 1. For example, the zone 2 right here, they rotate itself theta 2, but they different a little bit from theta 1. You see from S1 to S2 is pi over 2. It means they say the angle between the I minus 1 to Si. If we say Q2, it means the angle between the S1 and S2. S1 and S2, to matching the theta 2, S1 had to rotate negative pi over 2 from here to here. Okay, so when we fill in the table, we had to plus minus pi over 2. Q2 plus minus, it means minus pi over 2. How about for another example, Q theta 3 or Q3, how we calculate it? Before the H2 and H3 is matched together, it's the same. So Q3 is the Q3, okay? And theta 3 is no different. How about the F4? You know, how about the theta 4 or Q4? Q4 right here, you have to S3 and F4 the same. So Q4 is Q4 itself. No different between the previous frame. So, and S Q5, Q6 is the same because the S is matched together or parallel. So, so we will return this one on the filling the table on the DS table. So we already understand really a little bit about DS convention, how to, and two things I really concerned when you design the coordinate frame on the zone, you have to remember, try to do for for example, the other condition right here. The condition, yeah. The DS convention that have the condition for you want to design the frame I, and you had to know the previous frames. The condition is mean the SI had to be perpendicular to the SI minus 1, and SI intersect to ZI minus 1. For example, right here, look at it. For two zone 2 and 3, H3 always perpendicular with Z2 and intersection with Z2. You see? That's a condition. You have to remember, try to do that. And so the problem in the KUKA how to create a homogeneous transfer function, a transfer matrix from zero frame to reverse frame right here. So we have the total 0 to 1, 1 to 2, the matrix multiply together. I mean, look like the decommission for two link. We have the link 0 to link 1, 1 to 2, 2 to 3. We multiply all to all matrix. We got the total homogeneous transfer function, transfer from 0 to Reaper. Right here, we have the two coordinate right here from green and yellow. Yellow is mean we design with the decompression, but green right here for simulation into the raw system, and URDF. They use the URDF file and create the gripper with this coordinate. So to get the correct this simulation for raw system, we had to transform the yellow system into green system right here. It means we had to multiply to the matrix rotation to get this coordinate. So for any, go back to the problem right here. For example, for KUKA, you have the UREF or sacral. They design about the arm, the distance between the zone to zone. Okay, the link, something like that, the line of the link. Okay, you already know. And for example, if you see the problem with the Kinova arm or the UR10, you also have that file, and you can open it and you check. Right, that's the URDF on macro file. The for simulation, you can see that's parameter, that's the number, how the length, how the SYZ for each shown, and the distance between the frame, each frame. Right here, look at it. Look at it. This one, you know how the different link one from the base link right here 0, but from link 1 you had to move up for Z 0.33 okay meter, okay, or Z direction. Okay, theta zone 2, you see they have to S and YZ to move to the S and 0.35 and move up 0.42. Similar, you can for the kilogram or for something UR10, you can see that the sacral file, URDF file, and you can read this for information for all the linear zone. Okay, and next you can see something like this. Summarize this picture. You can see that fixed pay is mean base link right here is the table, is a ground or where you put link to the arm. Okay, this fixed link, fixed base. So and continue. Zone 1, zone 2, zone 3, zone 4, zone 5, zone 6, okay? And we put the coordinate 0, S, Z, 0 right here. And you know, you use the your right hand and you can see the Y, but Y right now we don't care so much right here. We just only know S0 and Z0. For example, for this zone 1 right here, they have the base link here, they have tri-link 1 and 0, and move to 0.33. Look at the URF side right here, from distance from here to here, 33. Okay, Rob is your no. We similarly we go to zone 2. Zone 2 the move to the S35 and and go up to the 442. Okay, right here to here, and continue. We go to the zone 2, zone 3 right here. Zone 3, this means they go up to the Z. Okay, right here, and 125. And zone 4, you can see this. There you go, this 1.6, but go down compared to the previous one. Just go down negative 0.0045. Okay, and you can know it about that. Okay, look at it. You can see the compared to the coordinate together, the difference from the coordinate. Okay, from there you can see right here SY for Z for coordinate 1. You see, look at that. You see, Z0, but you call O1, O0, O1, O2, and you can draw it, and you can know the this information from the URDF file. And you can fill in the table quickly with link 1, 2, 3, 4, 5, 6 and group per 7. Okay, and you know the alpha A, D, Q for each link. You know that time I mentioned right here, right? It's easy, right? And for example, the for link 1, for the link 1 right here, how to find the D1? D1 mean here the total distance right here, from here to here. Okay, 3 mean 0.23 plus 0.42. You got the D1. This one is good looking for you're thinking about. Okay, really good look for this one. You can easily understand for this picture. Link 0, link 1, link 2, link 3, link 4, link 5, link 6. And you can see A1, D1. D1 is mean the blood to this dimension. A2, A3. Very easy to see that. And look at the URDF and you can write down. And as I mentioned before, 1, 2, 3 zone create a spherical zone, horizon, so we can combine 3 coordinate frame into one at 5. Here at 4, 5, 6, and you see that T from bring here to the table for 1.5 D4 and this is right here. The total distance from here to here. This is from 0303. Okay, so after we already have the DS table, we go to the calculation, the forward kinematic and inverse kinematic. I had some file, the Python file, Python, the code Python in the link in the video. You can download and play into the Python. Because they use a lot of symbol library, so in your Python you should download the symbol if you have MATLAB, you can use the MATLAB, but you can use the Python too. But in the Python, if you don't install the Python, you can go to Anaconda and Anaconda 3. Let's go to the website, download, and in launching the Spider. In Spider, you have all you need. You don't need to install anything there, and it's really good. For example, for the forward kinematic KUKA right here, you see they also have the data table right here. When you fill in the all information, the data table, you but right here you remember in the Python or MATLAB they are simple function. It means symbol right here. You use the symbol. After that you replay with the value you want, create a results. And after that you define the transformation matrix from 0 to frame 1, 1 to 2, 3 to, and multiply all the frame. You create homogeneous transformation matrix. Right. As I mentioned before, because the DS convention coordinate and the coordinate gripper in the ROS is a little bit different, so you had to rotation. You had to here two different orientation, so you had to rotate the yellow one to matching the green one, left for simulation. So the correction, so total you have, you see, T07 times T correlation. Correction mean Y and Z because they need two steps to match to coordinate. So right here you have the transfer formula, and after that you can play with this metric. You fill in the from theta 1 to theta 6 any value, so they create the position for you. For example, 0, 0, and you run it. Okay, in the Harmon transformation metric, you had to know the first column, second column, and third column, and this metric really important. They show you for the right here the position 2.1530 and 1.9456. It means S, Y, Z and effector. And from 3 by 3 right here, now from 3 row 3 column on this matrix is the orientation. Okay, it's really important. For example, you change right here 3.5 for theta 2 and 3.2. Let's see how they create a new position right here. You can see you can get the position XYZ for the any factor. That's a forward kinematic. You know all the theta horizontal angle. You can find quickly the location of the any factor, the position and orientation of the last position, the last drawn reaper. So you can download for the link. You can play with it. Some basic code, okay, in the Python.